Okay, so we've made lots of good progress there on the activity, and we're going to sort of bring everything to a head here and generalize what we did with our demo. Number one, here's the notation for finding the left and right sums as you did in the activity. Warning, lots of notation ahead. Okay, so let's take a look at our picture. We're going to imagine that this purple looking thing here is a velocity curve. So that's why it's called v. It is just some function f of t, where t is time. The first few velocity curves that you dealt with the zombies were just lines, right? Horizontal or diagonal, uphill or downhill. And then I gave you a more complicated parabola looking thing, but it didn't matter. It was just some curve. And so here's the most generic thing. In the zombie races, the time went from 0 hours to 5 hours. We're going to generalize that too, and we're going to go from A to B, starting time to ending time. Okay, but what we're going to do is we're going to take this interval from A to B and we're going to cut it into a bunch of pieces. Now in the zombie race, the first thing you did was you did every hour for 5 hours. So that was 5 pieces. But then I said go every half hour. How many pieces did you have when I said go every half an hour? You had 10 pieces, right? And so we're just generalizing the number of pieces. So we're going to say n is the number of pieces, n equal pieces, and we're going to give names to these points here, these time values. So we're going to call the original, the start time, t sub 0, 0 for start, and then t sub 1 and t sub 2, and all the way up to t sub n is the last one. And so for your example, going half an hour, it was 0 there, and then it was a half, and then it was 1, and then it was 1.5, and then all the way up to 4.5, and then finally 5, right? 10 pieces down there. Okay, so the width of each interval is, let's figure this out here. Delta t is our symbol for change in time. If I tell you, for example, that we're going from 0 to 5 by half hours, is that what we did? Sorry, that's not what I meant. 10 pieces. How would you figure out how long each piece is? You divide the 10 pieces, sorry, divide the 5 distance that you have by the 10 equal pieces, and you'd come up with 5 over 10, or half an hour, right? What if instead of 0 here, it was 1? Now you have 4, and you're cutting it into 10 equal pieces, right? So all you're supposed to do is subtract to tell you how long the horizontal thing is, and then you divide it into the right number of pieces. So we're subtracting. The ending value of time is called B. The starting is called A. We are going to subtract them, and we are going to divide it into the right number of equal pieces, which we just called N. So the width of each of our little intervals is B minus A over N. Okay, and then we're going to start approximating. Now in the zombie race, you found underestimates and then separately found overestimates. Okay, you could do that. Instead, what we're going to do is just decide to pick the left-hand point in every little one of our subintervals. Sometimes it'll be an underestimate, sometimes an overestimate. That's okay. But for example, between like this point and up here, this point, if I just decide arbitrarily, I'm going to pick the left-hand point every time and assume that's the constant velocity, then in this case, have I over or underestimated the actual velocity? Under. That green thing is under the purple curve, right? Okay, but then the same kind of thing if I decide I'm going to go down here and I'll say here's one point and here's the next point. And in this case, if I pick the left-hand point and I assume that the velocity is a constant up there, is that going to be an over or underestimate from reality? That's an over, right? So we're just going to, for simplicity's sake, decide we're just going to always pick the left-hand point just to be consistent throughout, or just as well, always pick the right point. But we're no longer worried about always picking the over or always picking the under. Okay, so if I wanted to know how far we traveled in this very first rectangle, so we know we've been using our fancy formula, distance is velocity times time, so that's what we're doing here. Distance for that first rectangle. What's the velocity? Well, the velocity is however long this thing is, right? That's what we're assuming the speed is. And this is a function. And we know how to find the y value of a function is you plug the x value into that function. So this velocity is f of what input? Not just t, because t is sort of generic, but specifically t sub 0, right? That's the t sub 0 point You just plug that t0 into your velocity function. That tells you how fast you're going. And so this guy here becomes f of t0, that's your velocity, times the time that elapses in here. Well, it's t1 minus t0, but all of these times are the same. And in fact, we came up with our fancy formula b minus a over n. That's the time. It's like half an hour. And we'll just symbolize it with a delta t, half an hour. We're just calling that thing delta t. I warned you, right? Lots of notation ahead. So I want this to be really clear, though. This is a velocity times a time. It's lots of symbols, but it is just a velocity times a time. And then we can look in the second interval. And in the second interval, there's my estimate using the left-hand point. What is the velocity now? F of t sub 1. So the new velocity is f of t sub 1 times time. How much time elapses here? Still calling it delta t. It's the same amount of time. It was the same half hour throughout that problem. And so I've done two. I'm happy enough to say I found my pattern. It's f of t sub something times delta t. T0, T1, T2, T3, all the way to, the only funny business is at the very end. So let's take a look here and here. If we are picking left-hand points in every interval, which one are we picking? The Tn minus 1 or the Tn? Tn minus 1. In this case, it happens to be an underestimate. We don't care. We're just following our pattern. And so the very last one would be f of Tn minus 1 times delta t, just following our pattern, right? And so each of those little expressions represents our estimate for the distance we travel in that little time interval. And so we just add up all of these distances, just like you added up 5 or 10 numbers to come up with the total distance. And so that is all written out right here. So just confirm it's exactly what we wrote. Delta t f of t0, that was our first one. Delta t f of t1, that was our second one. Dot, 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 all the way to the end where it's not t sub n, but t sub n minus 1. Okay? That's picking the left-hand point. Just as well, we could pick the right-hand point. There's actually hardly any difference between picking the left or the right. In this first interval, what do you pick? T0 or T1? You pick T1. In the second interval, T2. Okay, there they are. T1, T2. Again, the only funny thing is at the end. Which one do you pick at the end? T sub n. That's our last one. And there's your T sub n. And so the only change between the left-hand sum and the right-hand sum is that the left-hand sum has a T0 and the right-hand one does not. But the right-hand one has a Tn, which is one thing past where the left-hand one stops. So it's only one term different between those two. Okay, so one other observation here. Let me just go back for a second to, this thing here. Suppose that I'm looking between 1 and 1.5 hours in, these two things here. And suppose that I pick the left-hand point to determine how fast I was going. So I guess that means I'm up here at like 1.2-ish, something like that. And I'm going to draw this picture. I'm going to keep drawing straight down here and straight down here. I'm going to ask you, what was the calculation? Let's call that 1.2. What was the calculation for how far we traveled in that time period there? Yeah, so it's a velocity times time, 1.2 miles an hour times how much time? 0.5. Okay, I don't actually care about the number. But what if I asked you a completely separate question and I said, find the area of that green rectangle? What's the calculation? 1.2 times 0.5, right? It's just the height times the base. And so we'll make use of this in our next class, but the fact is, if you want to find your estimate of the distance traveled, it's exactly equal to the area of that rectangle. And there's nothing special about that specific rectangle. Yeah, this would be an overestimate, but it's an estimate. Okay, so estimating the distance traveled is exactly the same as finding the area of the rectangles. Okay, so last complication here is number 5. What happens if the velocity is negative? So let's go ahead and find the distance between t equals 1 and t equals 4 in this picture. So let's go ahead and mark our endpoint. So t equals 1 is here. That's our start. T equals 4 is here. That's our end. Let's first describe the race that this person is running. In the beginning, they are traveling 4 miles per hour, and then maybe 2 miles per hour, and then 0 miles per hour, and then at the end, -2. I'm just sort of picking a few points arbitrarily. -2 miles an hour at the end. So what does that mean was their strategy? In the beginning, fast, right? And then slowing down until t equals 3. What's happening at t equals 3? Stopped, right? Are they turning around? At t equals 3, they are about to turn around. They're about to run backwards. At t equals 3, they are paused, momentarily, stopped. And then they start running backwards, or they turn around. And at first, they're running pretty slow. At t equals 3.1, they're running pretty slow, but then they speed up until they max out at -2 miles an hour. So fairly fast backwards. Well, that's a good question. Is there a way for us to know where they ended up? Because they made some good progress going in the right direction, and then they lost some progress going in the wrong direction. Well, let's see if we can answer Ryan's question. Let's figure out how far we traveled in each of these 2 different regions here. This one, and then separately this one. And so we know, big conclusion from all the work that you did is that if you want to find the distance traveled, you are interested in the area under the velocity curve. Area under the velocity curve is the distance traveled. So let's find the areas of these 2 triangles. We're not going to do the estimating game. We're not going to draw, you know, like in this first hour, you could say, okay, let's overestimate and say we were traveling 4 miles an hour the whole time. We can just find the area exactly. Okay, so the area of the blue, half base times height is good. Half, what's the base? Try again. 2, right? From 1 to 3. Half of the base times the height, 4. So altogether, 4 miles. That's how far we ran in those 2 hours. And then we turned around. And let's go ahead and find this area. Half what times what? Half the base is 1, height is 2. You could call it that. I'll call it positive. So 1 mile per hour. So how far are we from the start? Sorry, 1 mile, not 1 mile per hour. So that's 1 mile going the wrong way. Okay, so let's actually answer 2 different questions. First question, distance. Second question, displacement. So if you've had physics, you know the difference between these 2. If not, we'll define them. Distance is how far you ran. Doesn't matter forwards or backwards. It's just how far did you go. How far did we go? 5 miles. That is how far we traveled. That is the distance traveled, yes? 5 miles. 4 plus 1. 5 miles. But the displacement is how far you are from the start, which is 3. So that's a 4, and then -1. You could call it a -2 back there. 3 miles from the start. Okay, so 2 words both start with D, and they both mean similar things, but they're really quite different. So in the course of your lives, you have large distances, right? You have walked, you have run, you have biked, you have driven, maybe you have flown, you have traveled. That's your distance. If you were born in Greenfield, your displacement is probably like less than 3 miles, right? Like you're born at Bay State Franklin, your displacement for your entire life is about 3 miles. That's how far it is to that hospital, okay? No, it's just a definition. Just a definition. I went out, I ran 10K the other night. What was my displacement? I ran a 10K the other night. What was my displacement? At the end of all that effort, 0. My displacement was exactly, where was I going? Oh, I was born in New York. All right. Okay, so we got 5 minutes left. Let's go ahead and go back to wherever you were in the activity or the even more practice.